So last class what we did was I got stuck with the solution to two-body problem. So part 1, we start with the two-body problem itself, which is r double dot plus mu over r2 r is equal to 0. We take this and what we did was
pre-crossed it with H.
we pre-crossed with H. Post cross the above with H. What is H?
R dot R.
What is H? Angular momentum. Specific angular momentum. And then we arrived at this result. The result was R dot cross with H minus mu R divided by R is equal to C. So this was the first result, part 1 result. Okay. And here this C is called the Laplace vector. Now what you should know about the Laplace vector is, and that's what I was trying to prove. If you dot, so what happens if you dot this with, where is this r dot vector? Now always think about the board as the orbital plane. Okay, where is this r dot vector? R dot is on the board. Okay, if this is the orbital plane, if the board is the orbital plane, your R would be here, somewhere here, okay, and R dot would be like this, right? This, where's H? H is coming out, okay. Now if you cross these two, now what that means is this and this are perpendicular. And if you take the cross product, if you dot it with H, you're going to, so if you take the cross of these two, it's going to be
R dot.
It's going to go back into the board. Okay? That vector, this vector is going to go back into the board. And if you take the dot of that with this H, that will be 0. Okay? What it means is this vector C is in the orbital plane. The Laplace vector is in the orbital plane. Yes?
When you crossed it with H, how come you didn't bring down that other dot for the R? Since you started out with R double dot.
No. What we did was we crossed it with H, okay, and did some calculations on that. That we did, and then we got this result.
Alright.
Okay. So this is the simplified result. So that is in the video lecture, and it's in the textbook as well. Page 75, you'll find it. Okay. That's what it is. So this Laplace vector is in the orbital plane, and that is the kind of knowledge that will be tested when you do for your exam. Okay, this cross product, dot product, where the vectors are, that's what your understanding has to develop, and that's what this assignment, the first assignment is about. Okay, so this Laplace. Now try to understand. Try to go. If you don't understand this, review this. Why this Laplace vector is in the orbital plane. Okay. So part B, what we're going to do is, or part 2. Rearrange some number of equations. And when I say rearrange, what we do is divide by mu. So what you're going to get is vector r divided by r plus e is equal to 1 over mu r h. Okay. So here what I did was I just divided this whole thing by mu. This would be on the right hand side. You see this? R dot crossed with h. You can see this. Okay. This e, vector e is nothing but vector c divided by mu. Okay. This is simply, if you divide this, I take this on the right hand side, and this becomes positive. Okay. So you get this. Now what we do is, let's call this equation A. Dot equation A with R. Okay. What we're going to get is, we get R dotted with R divided by plus E dotted with R is equal to 1 over mu Now this one, what is R dotted with R divided by R? This is simple.
That's the distance, isn't it? The distance between
That's the unit.
So this, what does this result in?
A unit. A unit.
It's R squared divided by R. It's just R, right? So this would be just,
But that's scalar.
What
is it?
this will result in R. Okay.
That's R squared.
You can write this term as E R cosine theta, right?
Yeah.
Where theta is the angle between E and R. Okay. Now you have to solve for this. Right hand side, 1 over mu r. So can I write this as 1 over mu h dotted with so what I've done here, I've just done a cyclic rotation. Okay, the A dotted with B cross C is C A B. I've done a cyclic rotation. So this would be 1 over mu H dotted with H. Okay. So this is going to be equal to H square over. Okay. So what you can write is now R plus R e cosine theta is equal to H square divided by mu. So I take this R as common. 1 plus c cosine theta is equal to mu cos.
More solved than mu.
Huh?
What do
Where'd you get two H's out of all of a sudden?
He died.
this R plus R dot is H?
Oh, okay.
What was that thing that you said? What was that you were saying?
So this R dotted with R is what? R squared, right? R squared divided by R is what?
R. Okay.
That's R. Okay. So this ER can be written as
That's on the definition.
definition of dot product. This is the magnitude, the cosine theta. The theta is the angle between E and R. Now it so happens this is the solution to two-body problem. Okay. It so happens that solution to two-body problem is also equation of a conic section. You know what a conic section is?
It's like a
Conic section, yeah. What's a conic section? It's when you section the cone, you're right. So when you section the cone, so if I take this is a cone. If I section it along this, what are you going to get? Huh?
Not a cone.
If I section the section, you know what a section is.
Yeah.
What do you get?
If it's like a straight line, then it would be like a circle.
It will be a circle. So this will be a circle. If you section a cone, it will be a circle. Okay? Along the straight line, not parallel to the surface. If you section it in an oblique way, you get a ellipse. Sections are always 2D, two-dimensional figures. Right? Section, you have to understand what a section is. Section is when you cut it. You understand? Sectioning is, so when you section, you have to look at the top view. You section it and look at the top view. The top view of this would be a circle. The top view of this would be an ellipse. Okay. If you section it this way, you're going to get a parabol. You section it. So the hyperbola. Equation of a conic section. You can use equation of a conic section is generally this. R is equal to P over 1 plus E cosine. This is the equation of a conic section. That's a P, yes. That's generally called the parameter. Now what this means is what does this mean to you? Solution to the two-body problem. So the two-body problem is this. Okay, the solution is this.
So replace R.
You have found a solution for R, which is the R represents trajectory. Here,
Sorry, what is R represent?
trajectory R is and theta is let me explain that to you can you erase this part?
Yeah.
Let's look at an ellipse. Now let's say this is your R. Okay. This is that vector E. This. Now, what is this? What is this? This ellipse? What does this ellipse represent here? An orbit. Okay. This is an orbit, and it could simply be an ellipse. In the sense, it could be a geometrical figure. All right. What is the equation of an ellipse? You know what is the equation of an ellipse? That is the equation of an ellipse. You get it? This is the equation of an ellipse. This is the equation of an ellipse. This is the equation of a circle. This is an equation of a hyperbola, a parabola. What varies is E varies. If E is equal to 0, it's a circle. If E is it's an ellipse. If E is equal to 1, it's a parabola.
So that's not really the formula to define an ellipse. It's not really the formula for ellipse, it's the formula for anything.
Right.
It's defined.
So depending on what is E is called the eccentricity. You have heard about the term eccentricity? Yes. So eccentricity is nothing but a ratio of the major axis and the minor axis. Okay, what is the major axis here? Major axis is this.
Yeah.
Okay, and this is the major axis divides the ellipse into two halves. Right, this half and this half, but it runs along the it,
The focus. The focus.
right. It's the chord of the longest length. You can say so. Okay, that's the major axis, and this will be the minor axis. Okay.
So on that ellipse, you make the main axis
Now this E is the vector E. Remember when we developed this equation, here I gave you this vector E. When we did this, so for example, this E dot R, right? This, where is this vector E? This is that vector E. Okay. And this, what is this angle? Huh? It's this theta. So here you have to think about, we actually talked about this E dot R, right? E R cosine theta. This is that theta. This is the angle between E and R. Okay. Now what you have to understand is, what does Newton's or what does Kepler's first law say? Ellipses, right? So Kepler's first law says all orbits are of planets revolving around the sun are an ellipse. Now what this is, you have to appreciate the magic of mathematics. Without doing any observations, right? What Newton gave when Newton proposed the universal law of gravitation, it was not based on any observation, right? It was not. You cannot mathematically prove Newton's law of gravitation. Do you understand what that means? Can you mathematically prove laws? What are laws? Huh?
What about the second?
You cannot prove the second law either.
Proven theories.
Huh? It's not right. You can say it's proven theories, or what you do is somebody intuitively observes that, makes that observation repeatedly and says this has to be the law. And when Newton proposed that law, it was very intuitive for him. We couldn't understand, we couldn't get there. But that law was consistently proved when we did experiments. So when he proposed his Newton's law of universal gravitation, it was just a law, it couldn't be mathematically proved. So he gave mathematical equivalent of his law. And then what we have done here is, we used Newton's law of gravitation, we used Newton's second law to come up with the two-body problem. Okay? And the two-body problem, when we sought the solution for two-body problem, it came out to be the equation of a conic section. So what this means is, on one hand, Kepler did observations to understand or to say that all planets revolve around sun in an ellipse. But Newton's laws says the orbit could be any conic section. So Kepler's law is really just a special case of this. You understand? Everybody's following?
Yes.
Anybody not following? You guys? Jaylan?
So
Nathan?
the P in this equation is
So
just
P
equal
is h squared over
to, it's a constant.
It's a constant. So here if you think about what is h?
H is angular momentum, specific angular momentum.
Specific angular. This is the magnitude of specific angular momentum. Right? What do we know about angular momentum?
It's a constant.
It's a conserved or it's constant. So this is constant. What is mu?
That is just a constant.
That's a constant. Right? E is constant for a
In an ellipse.
for a given orbit or a given conic section.
Okay.
This is a constant. So if this r varies only because of this theta. The theta is only a function of time, and that is the reason r is a function of time. So if you know how theta is varying, you know how r is varying.
Is E a distance?
E is the eccentricity.
That's interesting. Oh, you said that.
E is eccentricity. Okay. So it's the ratio of the major axis and the minor axis. So what you should understand again, develop an appreciation for this. Okay. So again, look at Kepler's laws. What did Kepler's laws say? What was the first law say?
Ellipse.
Right. With the sun at the focus. Right. So here, this without doing, so Kepler spent how many years? Couple of decades to come up with this law, actually. 2-3 decades to do the observations and state those laws. And you can prove, so Newton came up with his laws, and just doing mathematics on those laws, you could actually prove Kepler's laws. So Kepler's laws can be proved. You know what that means? Can Newton's laws be proved? Newton's laws can also be proved using Einstein's laws. Einstein's theory of relativity. The more general the theory, so you see Kepler's law is just a specific case of this. You see that? Why is it a specific case? What specific case is it? Huh?
Condensation?
Huh?
Or condensation?
What is a specific case? Conic section is a general case. What is a specific case? Ellipse. He says ellipse in his first law. He doesn't say a conic section. He generalizes the law for, or he states the law for only ellipse and only. What does he specifically name in there? Planets, sun, ellipse. Right? He doesn't say. Does he say anything about moon? Does he say anything about artificial satellites? Does he say anything about outside our solar system? Does he say anything about asteroids? Does he say anything about comets? He doesn't know any of those things. Okay, he's only talking about planets and sun. Now if you look at this is Newton's law, right? We proved this using Newton's law. This encompasses planets, satellites, artificial satellites, comets, everything. This could practically explain the entire universe. You understand? That is the reason this is so important and so significant. Kepler's laws could only explain the motion of planets around sun, with sun at the focus, and only for elliptical orbits. Some of the comets don't follow elliptical orbits. Some of the asteroids don't follow elliptical orbits. Some of them follow parabolic orbits, hyperbolic orbits. So this, when you do it using mathematics, it explains everything in the universe. Okay?
What's the difference? I mean, I know you just said it, but what's the difference mathematically or something like that? I mean, it's an H.
I proved this, right?
Yeah.
So mathematically, I proved this. I started with the two-body problem. I proved it. Can you prove Kepler's law? This is actually Kepler's law is stated in this, right? But before Newton came,
It wasn't proven.
you couldn't start. Where do you start? Right? Did you have Newton's? You did not have universal. Where did we start? The two-body problem statement, right? Or how did that two-body problem statement come into place? Because of Newton's universal law of gravitation and Newton's second law. So before Newton came, where do we start to get to this point? We did not have a starting point. Right? Physics gives you that starting point. Mathematics lets you physics. Okay, the mathematical representation of physics, you can. That's how you prove. Do you understand what it means now? So you can start at. Can you prove E is equal to mc square mathematically?
Yeah.
You cannot. Where do you start?
It's also okay. It's not physical.
There is no more generic this thing to start with. So that's where something which universally defines everything. You see, when Newton came along, Newton was trying to define God. Okay, he was trying to give you very simple solution to everything in the world, and he was very close to doing that. His laws could practically explain anything in the universe. Forget about Kepler's laws, but it could explain practically anything and everything in the universe. Until we realized it couldn't explain the motion of subatomic particles. That's when modern physics started to come through. Now what this means is, again, an orbit could be any orbit. A circular orbit, an elliptical orbit, a parabolic orbit, or a hyperbolic orbit. Okay. Now what we need to do is, we have looked at you have to look at constants of motion. Okay. We have already looked at one constant of motion, that is angular momentum is conserved. Okay. Can you prove this? How do you prove this? If I ask you to prove this in the exam, how are you going to do this?
That's one equals to 0.
But how are you going to prove that? That's equal to 0, but you have to prove that that is equal to 0.
You have to cross it with R, the body,
Take a two-body problem and
cross it with R. Yeah, and then you get R dot double R equals 0.
right. So then you prove that V or VP of that is equal to R.
A.
Okay. So the next one is linear momentum is conserved. Okay. So what this means is NV is equal to 0. Or sorry. d over dt. Now you have to understand this a little bit. What is d over dt of mv? Can you see it, Imani? mv is linear momentum, right? What is Newton's second law?
This equals
F, right?
yes.
So what does this mean, linear momentum is conserved? Now I'm saying this is 0, but Newton says this is equal to F. Which is what is true? Huh? Is force equal to 0?
No, it's just transferred.
Huh?
It's transferred there.
What does linear momentum is conserved mean, or angular momentum conserved mean?
It means that there's a constant. So
Maybe no acceleration.
Huh? So when you
There's no force.
have to put, when you put constants of motion, you have to understand the law of inertia. Okay. So what does law of inertia say?
unless you place the timer to change the momentum.
A body?
A body motion will stay in motion until the outside force acts upon it.
Right. So here the constant body stays in motion, right? It is a constant until an external force acts on. You see that? So if this will be zero, the change will be zero unless there is an external force. Right. So that's what is conserved means. Okay. So if there is when gravity starts acting, that's when momentum will change. There's a change in momentum. So just like you have F is equal to d over dt of mv. What is this? What is here on the left hand side?
H.
Euro.
Oh, NA.
And he says not in yellow.
So that's inertia.
No, this is torque. A force affects change in linear momentum. A torque affects change in angular momentum. This is angular momentum, right? R cross mv is angular momentum. R cross v is what?
Is specific angular momentum.
Right. So R cross mv is angular momentum without the specific. So just like mv, d over dt of mv is f, d over dt of r cross mv is t. And again, you have to look at this in the context of inertia, law of inertia. So the angular momentum is conserved. R cross mv is d over dt of r cross mv is 0 unless acted upon by an external torque. Here it's torque. Okay. Now the third constant of motion is what could be the third constant of motion? Anybody? What else is conserved? Angular momentum is conserved, linear momentum is conserved, energy is conserved. Now I won't ask you to prove this part, okay? Linear momentum is conserved, but you'll be asked to prove angular momentum is conserved, and you'll be asked to prove energy is conserved. When you want to prove energy is conserved, what you do is you start with so here, this is a two-body problem. You dot with a dot. What you're going to get is alright. So this implies let's see, hand side which is d over dt of this. Okay.
What did you?
Now tell me if you want to follow this, okay?
How you cross that R? What did you do another R?
Now do these with me with this one. This is the two body problem. Okay? I just dotted this with R dot. This is equal to this. Here this becomes 0. Okay. Now I move this on the right hand side. What did I do here? This is the identity,
Oh, R.
the first one. Okay? So I just use that R, scalar R into R dot, scalar R dot. This R cancels with 3 and this becomes R square. Now here I'm going to solve the left hand side first. R vector R dotted with vector R double dot. This can be written as this. Why so? So just remember what we so d over dt of R dotted with R is what? R dot dotted with R double dot plus R double dot dotted with R dot. So it's 2 R dot R double dot. You understand?
You should write it out.
D over dt, so it's half d over dt of R dotted with R, it's half
R
dotted with R double dot plus
R dot.
R double dot. It's commutative, right? Or you can say double dot. It doesn't matter. Yes.
Are you strictly doing that side?
Left hand side. Yes.
Okay.
So this is equal to what? Half 2 times R dotted with R double dot. You see this? So I'm just saying this can be written as this.
The twos cancel.
Yeah.
You still have the two.
Huh?
Oh, there's no half on it.
There's
Where
no-
is it at?
Don't sleep, Michael. If we wake up, okay?
Since derivative, so you can take the half out.
Huh?
Since it's derivative, you can take the half out as a constant.
This one? No, but there I started with half.
You start
Oh, you
with half,
started
you
with
go with-
squared. You started with squared.
Where is square?
You start with half.
You can just take the half out,
Yeah.
and then just find the derivative of just, R dot,
See that you
dot part of R dot.
first R dot, times
I don't know
R
what I'm
dot.
saying.
Where did the two? Where the two come from?
Like this divided by
I'm
two,
saying
right?
this can be written as
That's
this.
part of it, okay. So it means the same thing on both sides. It's two.
You take the two,
Yeah,
up
then
and
I
I
just
just
divide
divide
it
by
by
two.
two. It's a constant.
So you can take.
Oh, you added it. Well, to make it right, basically, is what I'm. Okay, I get it.
Okay. Now the right hand side
It's hard.
minus mu divided by R square. Any doubts? Nia, you're okay? So this can be written as minus d over dt mu over r. Okay. Now do this for yourself. See if you can take the derivative of this and get k.
Quotient.
So now combine left hand side and right hand side. Okay. So what you're going to get is d over dt of vector divided by 2 minus d over dt of mu over r is equal to 0. This is actually
You said mu is a constant, right?
Hmm?
Mu
mu is a constant, right? So what happens is, if you take a derivative, mu will come outside. The derivative of 1 over r is minus 1 over r square, right? And since this is a, you have to apply the chain rule. You get this r dot. Did it?
Apply the chain rule?
You have to apply the chain rule. So now, what I mean by that is, if you have, what is derivative of theta square?
2 theta
2 theta,
d theta over
right? If theta is function of time. So that rule is applied here. Okay. Here r is always a function of time. So when I take the derivative, I have to complete that. Complete the derivative. Got it? This you have to keep in mind, please. Yes.
Why is that side positive?
Huh?
D over dt over r?
So this side is positive because if you see, what is the derivative of 1 over r? What is derivative of 1 over r?
Ln 1 over r squared. Negative.
Minus 1 over r squared. Minus 1 over r squared. The mu remains as it is. And you have, since it's a function of time, you have this r. So if I combine this, you get this, right? So what does this mean to you? D over dt will end with this. So this is, what is r dotted with r dot?
Scalar r times r.
It's vector dotted with itself.
Oh,
R dot square. You're right. So it's v square. Can I write v square? V square is okay. Divided by 2 minus mu over r is equal to 0. If this is equal to 0, the derivative of this is equal to 0, what does that mean? This is equal to? This is a
constant.
constant. So you can say v square divided by 2 is equal to absolute. What is v square over 2? Anybody?
And that's Q.
Huh?
And that's Q.
This one?
No, that's not Q.
This is absolute.
No, I was thinking about something else.
What is anybody v square over 2? Nia?
kinetics.
It is kinetic energy. It's specific kinetic energy. Half mv square is kinetic energy.
Where is it?
So m is, if it is per unit mass, it's just like per unit mass of angular momentum is specific angular momentum.
Okay, and then where did the
So this is the specific kinetic energy. This is the specific potential energy. Okay. This is the total energy.
Why is that potential energy?
What is potential energy?
It's mgh.
M is constant in mgh.
Yes.
H is constant. Sorry, G is constant.
G is constant.
What is potential energy a function of?
Height, distance.
Height. R is nothing but height. R is its radius, right? When you're in space, there is no height, there is the distance.
So that's almost like the Newton's gravitational constant.
It's not constant. It's a function of how farther away you are. So that is a potential,
Okay.
right? So if this is, so what it means is this epsilon is constant. If this is epsilon is the total energy, total mechanical energy. Okay, this here is kinetic energy. This is, and I'll explain to you why negative potential energy, and this is total mechanical energy. Yes. Mu is the, so you have F, remember this, F is equal to, F is proportional to M1, M2 divided by R square, right? So this is Newton's universal law of gravitation. Now what you do is F is equal to G M1, M2 divided by R square. For a given center, this can be written as G capital M small m divided by R square, right? Capital M is the mass of the larger body. Small m is the mass of the smaller body, right? And this R square is a relative distance between them. So what we do is we say for a given central body, when we are discussing a given central body, this G is constant, M is constant. If you're talking about Earth and any number of objects orbiting Earth, the G and M are constant. Right? Only this M is variable. So this Gm, excuse me, constant into constant is another constant. Got it? So if you have this mu is different for different central bodies. So if you're talking about Sun and any number of planets around it, that mu is a constant. If you're talking about Earth and any number of planets around it, it's that mu is a constant. Okay, so this proves that total mechanical energy is conserved. Now it's G.